Hello students, today we will discuss about modern theories of covalent bond. Before I start my video, I do request you please do follow, share and like my videos. If you are new at this channel, please don't forget to subscribe it. Alright, let's start our video. In the last video we have discussed about Lewis model. But there are some limitations about Lewis model, because classical Lewis model does not explain any geometrical and any polarities, bond distances and various energy transitions in its model, but it does explains that how atoms are bonded to one another. It also tells how the electron pairs are shared between the bonded atoms. But the logical question arises here: are these explanations just enough to justify the diversified world of molecules? And how do electrons avoid each other in spite of their repulsions? So the question is basically logical, so the answer should be logical. So what happened? It simply lies in the fact that the Lewis model seems to be an oversimplification. Shapes of molecules are very important because many physical and chemical properties depend upon three-dimensional arrangement of atoms. A true model should be able to justify molecular shapes, geometries, and arrangement of the atoms, and also bond polarities, bond distances, various energy transitions. So that could be simplified by spectroscopic techniques. This model should also make clear and unique behavioral features of the molecule during the chemical reactions. Alright, so there are some models that have been described here. First one is a valence shell electron pair repulsion theory. The second is according to valence bond theory, that is also VBT. The third one is molecular orbital theory. Alright, so this is also called MOT. So in this video we will discuss VSEPR theory or valence shell electron pair repulsion theory in detail. Valence shell electron pair repulsion theory, that is also called VSEPR VSEPR theory. So Sedgwick and Covalent in 1940s. Sedgwick and Covalent. So these two scientists pointed out the shapes of molecules that could be interpreted in terms of electron pairs or in the outer orbiter or valence shell of the central atom. But recently, another scientists like Nilholm and Gillespie, that is Nilholm and Gillespie, VSEPR theory, this one. Alright, so which explain the shapes of molecules for non-transition elements. So basically this theory is all about non-transition elements, the elements that does not change their shape and remain in the single state. Alright, so basic assumptions of this theory are: basic assumptions. Valence electron pairs or lone pairs or the bond pair, there are two types of valence electron pair. So the electron pairs that are present in valence shell are called valence electron pairs. So these could be of two types. First one is like they could be in a lone pair form, or they are bonded to any element. So lone pairs, first category, or the second category is bond pairs. These are in free state or these are in bonded state to any other element. So these are arranged around the central atom to make the distance maximum apart to keep repulsion at minimum. So you know, lone pairs and bond pairs are both are electrons. So you know, if these two pairs are present in the single valence shell, so what happened? These could repel each other. A force of repulsion create between these two pair of electrons. Force of repulsion. So to make this force of repulsion at the minimum state, what is this basic assumption for this model? These two lone pairs or bond pairs should be at the maximum distance. So this distance could be at 90 degree, 120 degree, 180 degree. It depends upon the structure of molecule. There are some postulates of VSEPR theory. Before I go through all of these postulates, let me describe the position of bond pair and lone pair. So basically this could be at 90 degree. For example, these are some bond pair and here is some lone pair. So these could be at 90 degree apart from each other of a single valence shell. Alright, so these could be in another form. This could be maybe 120 degree apart from each other. This is the lone pair and this could be a bond pair. Alright, so this is also present in the single valence shell of an element. Alright, so if it could be at 180 degree apart from each other, 180 degree. So here could be a bond pair or a lone pair. So this could be 180 degree apart from each other in the single valence shell of an element. Alright, so let's see about postulates of VSEPR theory. Here we describe the postulates. So the first one postulate describes about geometry. So what are the characteristics of an element that describe the geometry? First thing that is very prominent in a structure is geometry of a molecule. So what elements in a molecule that describes that play important role in geometry? So the first thing is lone pair and the second thing is the bond pair. So both the lone pairs as well as the bond pairs participate in determining the geometry of the molecule. So let me now write it down. Both the lone pair as well as bond pairs participate in determining geometry of molecule. Alright, so what could be the second postulate of this VSEPR theory? Arrangement of electron pairs in a polyvalent atom. So this is a basic question where, so in which arrangement the lone pair and bond pairs are arranged. So the electron pairs are arranged around the central polyvalent atom so as to remain at the maximum distance apart to avoid the repulsion. So if it is a polyvalent element, polyvalent means polyvalent atom. If it is a polyvalent atom, the lone pair and bond pair should be of central present at the central atom valence shell to keep the distance apart from each other at the maximum point. Alright, so let me write it down. The electron pairs are arranged around the central polyvalent atom so as to remain at the maximum distance apart to avoid repulsions. Alright, so here's the third one postulate. Which pair occupy more space, the lone pair or the bond pair? So the third postulate is like the electron pairs of lone pair lone pairs occupy more space than the bond pairs. Definitely, lone pair occupy more space. The reason is here. Let me explain it more in proper way. Like, if this is a molecule, here are some lone pairs. For example, this is a lone pair, and here is a bonded pair. There is a sharing bonding pair. So you can see here is bond pair. So bond pair is attracted from both of the nucleus of the two elements or the two atoms that have been bonded with each other. That's why it has maximum or it has minimum loop, or it has to bound at the restricted area. But the lone pair, if we talk about the lone pair, this one lone pair, it is free. This pair is free as compared to bond pair because it is only attracted by the single nucleus, and it has the maximum loop area to move around than the bond pair. Alright, that's why lone pair occupy more space than the bond pairs. I hope it will help you. Okay, so these were the postulates, and the last one postulate is fourth one postulate is like 2 electron pairs of the double bond and the 3 electron pairs of the triple bond contain higher electron charge density. Therefore, they occupy more space than 1 electron pair of the single bond, but behave like single electron pair in determining the geometry of the molecule. This is because they tend to occupy some regions between the two nuclei like the single bond. The 2 electron pairs of a double bond and the 3 electron pairs of triple bond contain a high electron charge density. Therefore, they occupy more space than the single electron pairs. Alright. So, but these behave like a single electron pair in determining the geometry of molecule. This is because they tend to occupy the same region between two nuclei like the single bond. Because if I draw the fourth postulate, if this is the first element and this is it has 3, or firstly I describe with 2 bond pairs, the second electron pair, it has 2 bond pairs. So these have the same region to occupy as if I draw the 3 or the single one If there are only single bond pair present between two elements, so they have this specific area to occupy. Alright, so if it has more than 2 or 3 bond pairs, so the same area is present to occupy by these bonded pairs. So they cannot move like to occupy this area or this one. So there is a specific area in this case where 2 electron pairs are present. And here the single electron bond pair is present. So what is the result? Geometry will not change. In the case of like it has 3 lone pairs or 2 lone pairs, if it is a single lone pair, the geometry will be same. If it has the double electron pair or triple electron pair, the geometry will remain same. But what will change here? Change is only like because they tend to occupy the same region, that's why there is no change. Alright, so I hope you will get this point. Now let's move towards the VSEPR theory explanation, how we can illustrate this theory. Let's consider the central atom is A, and then another element, that is B. So according to the arrangements of the atom, like AB2, AB3, AB4, etc., there is different types of molecule. It depends upon the valency of A, that how many B are attached with that molecule A. So let's discuss about explanation. Here is a type A molecule and type B molecule. Okay. So what will happen according to if we describe according to the electron pairs and arrangement of the electronic pairs, there is first is category AB2. Alright, so the second category is AB3, the fourth one category is AB4. So these are 3 categories or types for a molecule, because there is one A molecule and attached with 2 B molecules. There is one A molecule that is attached with 3 B molecules. There is one A molecule that is attached with 4 B molecules, but the geometry could be different just because of lone pairs amount and bond pairs amount. Alright, so let's discuss about bonding and lones pair, bond pairs, lone pairs, and arrangement of electron pairs. So first we will discuss about bond pairs, then we will discuss about lone pairs, then we will discuss about arrangement. It has AB2, so there is one A molecule that has 2 B molecules attached with it. So what could be the procedure? There is two bonding pairs or 2 bond pairs. Like here is first bond pair that is attached with B, and the second is with another B. So how many pairs are in this molecule? 1 and 1 another. So total is 2 bond pairs. Alright. So is there any lone pair present? No. In this state there is no lone pair. So how many bond pairs? 2 bond pairs and 0 lone pair. So what could be its geometry? Its geometry could be linear, in linear shape. Its geometry in linear shape. Alright, this structure could be in this state. Let's move towards the AB3 type. So if there are 3 B molecules are attached with A, first A, and there are 3 molecules of B, so it could be like B, B and B, because if it has three molecules bonded with with the A element, there are three bond pairs. Three bond pairs because first pair, second pair, and third pair. So total bond pairs are three. Here we should write here AB3. Three bond pairs. In the first molecule, there is zero lone pair because all the molecules, all the electron pairs are attached with the elements and are bonded, so there is no lone pair, so zero lone pair. So its geometry could be trigonal planar. Its geometry is trigonal planar. So its best examples are like BH3, BF3, AlCl3 or SO3. I should write here BH3, BF3, AlCl3 or SO3. So basically the distance between the two B molecules is 120 degree. Alright. So this was the AB3 with three bond pairs. Alright. If it has two bond pairs and one lone pairs. Two bond pairs and one lone pair. So what could be its geometry? Two lone pair and one bond pair. We should remove this first one B, and there should be a lone pair present that is not attached with any other particle or any other element. So what happened? What could be its geometry? Its geometry is like this slide. A, B particles attached with B particle, and the distance is less than 120. So the whole area is covered by lone pair, because you know lone pair occupy more area than bond pair. So the distance between two bond pairs is less than 120. So these examples are SN, Cl2 and SO2. If we move towards the AB4 type, I mean like one A molecule and four beta molecule. So there could be three types of category. The first category is like two bond pairs, two lone pairs, three bond pairs, one lone pair, four bond pairs, zero lone pair. So there are three types of categories. Let me describe step by step all of this. Alright, so if I describe 2 by 2 category, so this could be bent or angular. Like A has two lone pairs and two bond pairs. Alright. So the angle between B particle is less than 109.5. Angle should be less than 109.5 degree. Alright, so its examples contain like water molecule, H2O and H2S and NH2. If we talk about three bond pairs and one lone pair, so what should be its category? It has like A with one lone pair and three bonded pairs. So its category should be in this type, geometry should be in this type, and the angle between two B particles or two B atoms is less than 109.5 degree. Alright, so this is the category, and examples contain NH3, NH3, NH, NF3, NH3, NF3 and PH3, etc. So these are examples. So its geometry is trigonal pyramidal. If we talk about 4 bonded pairs and 0 lone pair, it means like 4 B particles are arranged with A, first B particle, second B, and the fourth in. So there is 0 lone pairs. Angle between two particles is 109.5 degree. So this is basically tetrahedral geometry, and this type of molecules contain CH4, SiCl4 and CCl4 and BF4. Okay, so and another one is like SO4. So this was the basically explanation of VSEPR theory. Then we will discuss in detail molecules containing 2 electron pairs, I mean to say like AB2 type. So here is the molecules containing 2 electron pairs, AB2 type molecule. If we consider a molecule that contains a particle A that is connected with 2 molecules of B, so in such molecules 2 electron pairs around the central atom. For example, these 2 electron pairs, this one, with the central atom are arranged at far distance apart at an angle of 180 degree in order to minimize the repulsion between them. For example, here is a bonded pair and here is also a bonded pair. So these 2 bond electron pairs are apart from each other at the maximum angle to minimize the repulsion between these 2 pairs. So here are some examples of AB2 type molecule. The first one is beryllium chloride. So beryllium is a central element here, and the chlorine, 2 chloride ions are attached with this molecule as a B type. This is the B type and this is the B type molecule, and there is central element A. So at the angle 180 degree, these 2 B elements are attached. The next example is magnesium chloride. The second one is calcium chloride, cadmium chloride and mercurous chloride. So what are the geometrical composition? Magnesium will be the central atom, and chlorine as the same as in beryllium chloride as a B type molecule, as a B type element. So here is a A1. So it could be like this: A, B particle and B particle. There is the distance between these two is 180 degree. As same as above molecule, calcium chloride geometry, it has the angle of 180 degree. So here is a bonded electron pairs. So these 2 electron pairs are at maximum distance apart from each other to minimize the repulsion between these electron elements. So what are the basic points? It has a linear geometrical molecule or linear structure. You can see this is in a line, so angle is 180 degree. So this is called the linear structure, linear geometry, and it has 180 degree angle apart from each other, and there are 2 electron pairs. Alright, so this is the AB2 type molecule. So next is AB3 type molecule. Molecules containing the 3 electron pair, AB3 type molecule. It has the 3 types of molecule composition or geometry. For example, if it has AB3 with no lone pair and 3 bond pairs, and another one geometry with the AB3 with 1 lone pair and 2 bond pairs. So we will discuss step by step. So in such molecules, central atom contains 3 bonding electron pairs which are arranged at maximum distance apart at the mutual angle of 120, giving a triangular planar geometry. So if we draw a circle, it has 360-degree angle. So if it has 3 bond pairs, so there are 3 bond pairs. So simply, if you want to put these 3 bond pairs at the equal and the maximum distance from each other, so simply you have to divide 360 by 3. How many bond pairs are present? 3. If there are 2 bond pairs, so you have to simply divide by 360 by 2. If you have 3 or 4 bond pairs, so simply you have to divide 360 by 4. So the answer will be their distance, maximum distance. You have to keep these bond pairs apart from each other. I hope you get my point. So if in such molecules 2 electron pairs around the central atom are arranged at further distance apart at the angle of 180, if you divide 360 by 3, you will get 180. So each molecule, for example, here is a molecule, there are 3 B molecules are attached with this one. So these two, the distance between the two B molecule is 180 degree. Here is also 180 degree, and here is also 180 degree. So these are maximum apart from each other to reduce the repulsion force. Alright, so let's discuss about its examples. There is a BH3. Alright, so it has BH3 example. So if I draw B with 3 hydrogen elements attached with boron, so it has 120 degree apart from each other. Angle is 120 degree. So its geometry is basically trigonal. Triangular planar geometry. Geometry is triangular planar geometry. So same elements like ALH3 and BF3 and GAH3. These elements show the same triangular planar geometry, and elements are arranged by 120 degree with apart from each other. It has no lone pair, simply 3 pairs of bonded electrons. Let's move towards the next one, that is AB3 with 1 lone pair and 2 bonded pairs. If we take an example of SnCl2, so one corner of the triangle occupied by 1 lone pair and give rise to the distorted triangular structure. If there is a lone pair and there is a bond pair, like lone pair can occupy more space than bonded pair, so it will contain more space. Here is a bonded pair, here is a bonded electron pair. So this is a lone pair, so it will occupy more than 120 degree. So as a result, the angle between two bonded pair electron is less than 120 degree. Geometry is same as triangular planar. So it is the structure of vapor phase, because it has to giving rise to the distorted triangular structure of the SnCl2. Other than AB3 with no longer lone pair and AB3 with 1 lone pair and the 2 bonded pairs, there is a third structure of molecules containing 3 electron pairs, AB3 type with the multiple bonds. Let's discuss what is it inside this. Here is the AB3 type with multiple bonds. Example, take SO2. Here is an example. One corner of triangle is occupied by lone pair. You can see here is a lone pair and the two bonds, double bond with oxygen and another double bond with another oxygen is formed. So this is basically more than 120 and less than 120 angle here present. This is also a triangular structure, but if we take another example of SO3, the geometry will be basically triangular geometry, like if here is S, no lone pair with 3 double bond elements. Double bonds electron pairs are with oxygen, 3 oxygen elements. So it has also the same geometry like triangular planar geometry, and it has the maximum distance 120 degree apart from each other. So this is the third one type where the multiple bonds are present. Alright, so next topic is about AB3 type, AB4 type. From now to onward we will discuss AB4 type with the 1 lone pair, with no lone pair, with the 2 lone pairs, with 3 lone pairs, and more on. Here is the molecule containing 4 electron pairs, that is AB4 type. So the first category that lies in AB4 type is AB4 type molecule with no lone pair. AB4 type with no lone pair. Basically there is no lone pair, so A is a central element and there are 4 B molecules attached to central element. So there is the first one, second one, third one, and fourth one. So here is a fourth one element. There are 4 loops, 4 clouds present. So each cloud have 4 electron pairs. So just to avoid their electrostatic repulsion by drifting apart, so as to maintain a mutual bond length of 109.5 degree, such geometry enables to form a shape of regular tetrahedron. So this shape is basically tetrahedron shape. This is basically tetrahedron geometry. So let's take an example of carbon CH4. It has a tetrahedron geometry. If we write down its configuration, carbon number 6, 1s, 2, 2s, 1, 2px, 1, 2py, 1, and 2pz1. It has 4 subatomic orbitals that have non-paired electrons, so its valency is 4. So it has capability to make 4 bonds. So the 4 electron pairs are directed from the central towards the corner of the regular tetrahedron, like this corner, and 4 corners, with each apex representing a hydrogen nucleus. Arrangement permits the non-planar arrangement of electron pair. For example, if this is a carbon, here is a hydrogen one, there is a hydrogen nucleus, here is also hydrogen, and here is also a hydrogen nucleus. So the distance between two carbon hydrogen element is 109.5. For example, here is a hydrogen, here is a hydrogen. This distance between this carbon, hydrogen, and hydrogen element is 109.5 degree, and also this carbon and hydrogen element is distance is 109.5 degree. and you can see there could be four corners like 1 2 3 4 corners, and four faces like this one, first face, second, third and fourth face, and six edges, and six bond angles. Alright, you can see in the model structure there are four corners, four faces, six edges and six bond angles. Let's move towards another type with the one lone pair. Alright, so let's discuss with one lone pair elements. With one lone pair and three bond pairs. In such cases, charge cloud of lone pair electrons like non-bonding electrons spread out more because they occupy more space than the bonding electrons. So as a result, somewhat large lone pairs charge cloud tends to compress the bond angles rest of the molecule. For example, here is a lone pair and A-type molecule. There are three bonded pairs electrons. So what will happen? This will compress these three elements to tend them to make a place closer to each other to occupy more space. So what happened next? Here is a lone pair. It will occupy more space, and these three molecules or bonded electrons will come closer to each other. So there are some examples. For example, NH3 molecule. Here is a NH3. So it has one lone pair in this molecule. If nitrogen configuration is 7 1s2 2s2 2px1 2py1 and 2pz1. So here is the configuration of nitrogen element. So the non-bonding electron in 2s orbital takes up more space. For example, this is a non-bonding or lone pair. Alright, so s orbital contain our lone pair that occupies more space than these bonded electron pairs. So they tends to come closer with each other, and the angle from 109 and angle shrinks from 109.5 degree to 107.5 degree. Alright, the effect compels ammonia to assume a triangular pyramidal geometry instead of tetrahedral. So its geometry could be like this. For example, this is a hydrogen element, hydrogen another one, and the third hydrogen here. So angle should be 107.5 degree. So it does not contain tetrahedral geometry. It contains triangular pyramidal geometry. Triangular pyramidal geometry. So let's see another example for having similar effects are evident in the geometries of molecules. For example, PH3, ASH3, SBH3, BIH3. Let's discuss the structure of NF3. So here is another example, NF3. Again, nitrogen having a one lone pair and three bonded pairs, one lone pair and three bonded pairs. So angle will be 107.5. Geometry will be same as the last one, NH3 we have studied. Its angular geometry will be like a triangular pyramidal geometry instead of the tetrahedral like methane. So it compresses these three bonded electron pairs and occupy more space. So let's discuss the another one category of AB4 type with the two lone pairs and two bond pairs. With two lone pairs and two bond pairs. Presence of two lone pairs introduce three types of repulsion. First is like lone pair repulsion, lone pair bond pair repulsion, and bond pair repulsion. You can see if a molecule there is a molecule like if we discuss the molecule of oxygen O8, that electronic configuration is 1s2, 2s2, 2p, x2, 2p, 2py1, 2pz1. So it has like two lone pairs and two bond pairs. These are lone pairs and these will become bonded with another elements and become the bond pairs. So there are two types of repulsion. First is between two lone pairs. Two lone pairs repels each other, and another repulsion type is two bond pairs, between two bond pairs. So two bond pairs will repel each other, and the third type of repulsion is between lone pairs and bond pairs. First one is between lone pairs, second one is between bond pairs, and third category is between repulsion between lone pair and bond pair. So let's discuss about oxygen having 8 electronic number and its configuration is written here. If I draw its geometrical configuration, oxygen element OH and two hydrogen elements are attached with this, and there are two lone pairs are present. So these two lone pairs repel each other at the maximum state, and they will tend to occupy the more space than the bonded. So the bonded pair will shrink and come closer to each other. The angle between two bonded electron pairs will become 104.5 degree. Alright, so at this point VSEPR theory ends. According to VSEPR theory, we can explain lone pair and bond pair structure, their geometry, and also about arrangement of the central polyvalent element, or if we can explain about the space that occupy with the lone pairs or bond pairs. But there are some limitations. There are some limitation means that there are some characteristics that could not be explained with this molecular theory or molecular VSEPR theory. So what are those limitations? Let's discuss. So the first limitation is limitations of VSEPR theory basically predicts and explains the shape of molecules only, but does not give the reason the formation of bonds. It only explains geometry or shapes of molecules. but there is a limitation. This theory does not explain the reason why this geometry has happened, what is the arrangement, what are the formation of bonds and the shapes of molecules, but it does not explain bond shape, formation of bond, and shapes of molecules. So basically these are three categories. First one is bond shape, formation of bond and shapes of molecules. These could not be explained with the VSEPR theory, so it fails to explain all of these characteristics. So there is another one theory that is called valence bond theory, VBT. Also, so it helps us to explain all of these characteristics. So we will discuss VBT in the next video.